Hello, today I want to talk about physics, our reality, and the limits of knowledge. I try to answer what dark matter and dark energy could be and how a theory of everything would look like. How far can we get with our principles of logic? Physicists had been really successful, but now they have some difficulties to get any further. In this way, let's start with Kurt Gödel and his incompleteness theorem he published nearly 100 years ago. In other words, he proved that no system can be described in a complete way and that some parts always contradict each other. Or, in a very simple way, we can argue that our universe consists partly of irrational numbers, and because irrational numbers have an infinitely big amount of chaos, we would need an infinitely difficult formula to describe everything. So we will never find a solution for everything, but maybe we can still unite quantum physics and the theory of relativity. Let's take a look. In our world, normally it doesn't matter if you look at a mountain, a tree, or a face. In general, you get always the same amount of information. Now we switch to the very small. An atomic nucleus consists out of protons and neutrons, and the force that holds the electrons around it is again a particle, a photon. So normally you get something like layers, and that something consists out of something. But layers are never hard borders. It only means that the inside of a neutron has only little effect to our chemistry, like the planet Mars has only limited effect on our living on Earth. But we can imagine that everything affects everything somehow. An electron, for example, has its origin in the oscillating proton that is creating an interference pattern. The electron itself has no inner structure but behaves like a normal particle. Peering inside protons, it seems that there's an end. Inside, we detect quarks and gluons, and if we try to detect further details, we simply get new quarks and gluons. But because we are searching so deep, we have to accept that our understanding is only partly real, and in the same way, an illusion. As a conclusion, there cannot be something like the smallest particle, and the inner structures can be as complex as our real world. The big particle accelerators detected many different particles, but normally they are not detected directly. To extract the important information, we have to examine the decay to other kinds of particles. Huge quarks, like the top quark, decay into many smaller quarks. The measurements get more and more difficult, and more data is needed to prove something right or wrong. So scientists are using seldom but clean decays to find something new. We have to accept that we can only detect the right phenomena with the right kinds of measurements. It's not realistic that we can use gravity to detect quarks because the gravity force is much too weak. Now we pay attention to the big scales and the big questions. We are unable to explain the strange rotation velocities in galaxies with the visible matter. The rotation velocities in the outside regions of galaxies should go down, but often they stay constant. It looks as the arms of the galaxies are pulling at the stars like a rope and accelerating them. But it seems impossible to describe the effect with the existence of known particles. Our simulations are good, and we can detect so many kinds of particles in our universe. We can prove that in the whole universe the physical laws are precisely the same. So where's our fault? To describe the strange velocities, physicists added something we call dark matter. But to describe the effect, there's also a possibility by removing some space, or in other words, the speed of light could be even higher due to a lack of mass and gravity between the galaxies. The physical laws can stay the same. This would also explain the acceleration of distant galaxies and the expansion of the universe. The wavelengths would change because of the changing gravity field, and that would explain the redshift of these galaxies. In a way, the whole universe looks like a big gravity lens, and by the way, it's important symmetry that the world gets more and more simple and looks more and more similar around it if we peer further and further into space. Our understanding is real and right, and at the same time, it's part of an illusion, similar to our small quantum world. So we get to the next important question. What is information? What is a bit? We don't know. It's something symmetric and asymmetric at the same time. It's maybe the best, most compact way to describe something. I want to illustrate information and our three-dimensional space in a different way. First, the three-dimension feels a bit like a Lorentz force, interaction between a force, a magnetic and an electric field. But space is symmetric to all three dimensions, or more precisely, only equal to all three dimensions if there is no gravitational field and no acceleration. Here on Earth, we have so many particle interactions that only two dimensions are independent from each other. Things are falling down. In space, all three dimensions are independent from each other, but nothing can stand still. It would all collapse. Planets have many options to circle around the Sun. Because of their particles are attached to each other, they following only one line. And due to Albert Einstein, this is always a straight line in a curved four-dimensional space. We take into account that there is normally more than one explanation for a physical law. For example, it's possible to explain all relativistic effects by the image that the time itself is flowing from every observer into the surrounding space. Now we're coming back to the question what matter is, or even more important, what space is and why matter curves space. Matter is something that interacts with the surrounding particles, but maybe this is the only way we can think. We know that space is a symmetry where in three directions neighboring points have the same distance to each other. And if we accept that mass can curve space, the symmetry in the four-dimensional space-time is a constant speed of light. In quantum world, we also have symmetries because of the limited amount of quantum states. Two fermions never get to the same state, while bosons like the same state, and the chance that they are in the same state is doubled. So quantum physics tells us something why neighbors exist, something that creates structures like circles or spheres, because of its symmetries. But this is not the cause why our world has to be a three-dimensional space. There are more explanations, but surely space is the balance of symmetries for simple patterns. Mathematics is so powerful because it's also using a symmetry of the same distance of numbers. It's maybe the best way to describe patterns. For our three-dimensional space, imagine the symmetries in the pattern of the Pythagorean triplets. We can create a right triangle with the side lengths 3, 4 and 5, but if both legs have to be the same length, we never get a rational solution. Our world is not always symmetric, but there's a good chance that at least one half is symmetric. Maybe the other half is chaotic. Thank you for watching this video.